Okay, hello and welcome to a small demonstration of how to measure time kind of more accurately for algorithm analysis. Okay, so here's the situation that we had in one of our classes. We were trying to prove that a linear search was actually linear. Okay, so it seems like a pretty straightforward deal. So what we did was we wrote a linear search algorithm. Okay, it's just up here. I'm not so concerned about that. And of course, you want to try this for a bunch of different sizes of arrays. So I picked 100, 200, 300, so on, all the way up to 1,000. And just to avoid sort of the timing errors, I repeated the linear search like 1,000 times. So whatever numbers we get, you divide by 1,000, that'll be the actual amount of time. All right, so first of all, I'm starting the timer, or I'm grabbing the nano time just before the operation and just after, calculate the difference between the two, and of course that'll tell me how many nanoseconds it took in order to run the linear search. Well, 1,000 times. All right, so you have everything set up and you say, okay, great, I'm gonna go and run it. So you go ahead and you run it and you produce a bunch of results. Okay, now, I'm not sure if you can see from the results here what this is, but let me plot these into Excel. Okay, so we can see how this looks, and I'm going to paste this in, and we're going to split this up according to columns. Okay, here we go, and commas separated. Okay, here we go. And what we've got in here, okay, one more, here we go. This is going to be the top, and this is going to be the time. All right, so you're all excited and you say, okay, I think I've got some really cool things. I'm definitely going to see that this is linear, and I'm going to insert a scatter graph once I find it. There we go, scatter graph with some straight lines, and you go, what? That doesn't really look very linear. But you'll notice that there's kind of a bit of linearity here, and there's a little bit of linear here, but suddenly it drops completely in here. So what gives? All right, well, welcome to the optimizations that Java uses. You see, when you start to run a Java application, the entire application starts off in interpreted mode, and if you run only like a few hundred things, basically you're looking at just the regular interpretation. But what happens after you've run it for a while? The Java runtime environment looks and it says, hey, I think I can, this is obviously some hot code that's happening, and what it will do is it'll end up optimizing it by producing machine code and letting it run. And that's why we see this big sudden drop. And then of course everything continues again, which, okay, down here it makes sense, but it really doesn't make much sense here. All right, so is it possible to fix this? And the answer is yes. I think the easiest thing to do, well, apparently the typical thing is that you let the Java application sort of warm up first by ignoring the first few hundred of these, but there's kind of an easier way. So what I'm going to do here is I'll show you how to disable the just-in-time compiler within Eclipse. So here you go to coverage, I'm saying coverage configuration, sorry. We're looking for run configurations. Okay, and right here, I'm going to right click and say, give myself a new configuration, and I'm going to call this no JIT optimization. And here under the arguments, under the VM arguments, I'm just going to say run interpretive mode only. So that's an INT in case that's really, really small, just INT. Okay, so we'll go ahead and we'll click apply, and instead of calling this question 1, I'm just going to call it regular optimization. Okay, this way it'll probably make a little more sense. All right, so let's go ahead and close this. And now whenever you pick run as, you'll be asked which one do you want? Do you want the regular optimization or the no JIT optimization? Okay, we'll run this one, and we'll take a copy of these results, and let's go take a look at my my graph once again. I will delete these and I will paste these into the cell. Yeah, go for it. All right, and we will once again split this up. All right, and of course now what we've got is we've got ourselves something that actually looks like a real linear graph. Okay, so if you're trying to do other things, like you're trying to prove that a particular search within a hash table is constant, you could use things like this. So the problem is that you just wanted to be able to disable the optimization so that we don't get any of this sort of automatic hotspot swapping out going on.